Space, the vacuum we've always been told is silent, is actually filled with sound. Eerie melodies that tell the story of cosmic violence and creation. NASA scientists have recorded the actual sounds of black holes, and they are nothing like the dramatic vacuum whooshes you've heard in sci-fi movies. They are deeper, stranger, and far more unsettling. In fact, the Perseus galaxy cluster black hole produces sound waves so deep that they are 57 octaves below what the human ear can detect. That quadrillions of times deeper than anything you've ever heard. You might be thinking, wait, sound can't travel in space. There's no air. And you'd be partially right. Sound, as we experience it on Earth, needs a medium like air or water to travel through. But space isn't a perfect vacuum. It contains extremely tenuous gases, plasma, and other particles, especially around massive objects like stars, planets, and black holes. These particles, while incredibly sparse compared to our atmosphere, can still transmit pressure waves, the physical phenomenon we experience as sound. Scientists use two main approaches to hear the universe. First, they detect actual pressure waves traveling through these sparse mediums and convert them to audible frequencies. Second, they take electromagnetic data like radio waves or light patterns and translate them into sound through a process called sonification, which is like creating a musical score from visual data. Let's start our cosmic listening tour with perhaps the most famous space sound ever recorded, the eerie, deep note produced by a supermassive black hole in the Perseus galaxy cluster. In 2003, astronomers pointed the Chandra X-ray Observatory at the Perseus galaxy cluster, located about 240 million light-years away. At the heart of this cluster sits a supermassive black hole, which wasn't just silently consuming matter, it was creating enormous pressure waves in the hot gas surrounding it. These waves ripple outward like sound traveling through air, except they are propagating through a cloud of gas heated to millions of degrees. When NASA scientists converted these pressure waves to sound, they had to raise the pitch by 57 octaves to make them audible to human ears. That's not a small adjustment. It means the actual sound is quadrillions of times deeper than anything humans can hear. In fact, it's one of the lowest notes ever detected in the universe. Listen to this. That haunting, almost ghostly rumble is what a black hole sounds like. As the black hole feeds on surrounding matter, it doesn't consume everything. Some material gets superheated and blasted outward in jets, creating these rhythmic pressure waves that ripple through surrounding gas, essentially turning the entire galaxy cluster into a massive speaker. If you could somehow stand in the Perseus cluster protected from the deadly radiation and extreme temperatures, of course, you wouldn't hear this sound with your ears. The wavelengths are too long and the medium too thin, but you would feel these vibrations passing through your entire body, like standing next to a massive subwoofer playing a note far too deep to hear. Scientists believe these sound waves are crucial for understanding how galaxy clusters evolve. The energy carried by these waves helps prevent the cluster's gas from cooling too quickly and forming excessive stars, essentially regulating the growth of the entire galaxy cluster. But there's another cosmic sound that's been around since almost the beginning of time itself, known as a cosmic microwave background, CMB. This faint radiation permeates the entire observable universe and captures sound waves from when the cosmos was just 380,000 years old. In the early universe, everything was compressed into an incredibly hot, dense soup of particles and radiation. This primordial plasma was so thick that it actually transmitted sound waves, real physical pressure waves rippling through the cosmos. As these sound waves traveled through the early universe, they created areas of compression and rarefaction, essentially regions of higher and lower density. When the universe finally cooled enough for light to travel freely, these density patterns were frozen in place, imprinted into the radiation that we now detect as the CMB. Scientists have translated these ancient patterns into sound. This is the echo of the very first sound of our universe, the acoustic oscillations that help shape the cosmic web of galaxies we see today. The pattern of galaxies we see today, including our own Milky Way position in space, was influenced by these sound waves from the infant universe. It's as if the cosmos was shaped by its own primordial song. By analyzing these sound patterns, cosmologists can determine fundamental properties of our universe, including its age, composition, and fate. The CMB is essentially a fossil record of the universe's acoustic properties, preserved for billions of years. But let's turn our attention to some of the most accurate timekeepers in the universe, pulsars. A pulsar is a star with more mass than our sun compressed into a sphere the size of a city. This incredibly dense object spins hundreds of times per second, sweeping beams of radiation through space like a cosmic lighthouse. Pulsars are the remnants of massive stars that have gone supernova. During these cataclysmic explosions, the star's core collapses into an ultra-dense neutron star. As these neutron stars spin, they emit beams of radiation from their magnetic poles that sweep through space like lighthouse beams. When these beams cross Earth's path, our radio telescopes detect regular pulses, hence the name pulsars. When scientists convert these radio signals to audio, this is what you get. That steady beat comes from PSR B0329 plus 54, a pulsar about 3,460 light-years away. It rotates precisely 1.4 times per second, creating these perfectly timed pulses. We're literally hearing the ticking of cosmic clocks that formed billions of years ago in spectacular supernova explosions, and these rhythms have helped confirm Einstein's theories about the nature of space and time. But much closer to home, our own solar system is filled with surprising acoustic phenomena. The largest planet in our solar system, Jupiter, has the strongest magnetic field of any planet. And when it interacts with the solar wind and its volcanic moon Io, it creates remarkable radio emissions. Here's what Jupiter sounds like. Those otherworldly swoops and whistles were recorded by the Voyager spacecraft. They are created by charged particles trapped in Jupiter's massive magnetic field, spiraling along magnetic field lines and emitting radio waves. Perhaps most exciting are the sounds from Mars, recently captured by NASA's Perseverance rover, the first actual audio recordings from another world. Listen to this Martian wind. That's the actual sound of wind on another planet traveling through the thin Martian atmosphere. Scientists were surprised by how sound travels differently on Mars. High-pitched sounds attenuate much faster than on Earth due to the planet's unique atmospheric properties. These planetary sounds help scientists study things like atmospheric conditions and magnetic field structures. While these planetary sounds travel through gas and plasma, there's another, more fundamental kind of sound that travels through the fabric of space-time itself, gravitational waves. These are ripples in the fabric of space-time itself, created when massive objects accelerate or collide. Einstein predicted these waves over a century ago, but they weren't directly detected until 2015, when the LIGO Observatory recorded the collision of two black holes 1.3 billion light-years away. When scientists converted the space-time ripple into sound, here's what they heard. That distinctive chirp represents two massive black holes spiraling together, moving faster and faster until they merge, a cosmic collision that released more energy in a fraction of a second than all the stars in the observable universe combined, yet was detected as the faintest whisper by our instruments. Think about what's actually happening here. Massive objects distort space-time itself, sending ripples outward at the speed of light. These ripples slightly stretch and compress everything they pass through, including you and me. During a strong gravitational wave event, you literally become slightly tall and shorter as the wave passes through, though the effect is far too small to notice. These gravitational wave sounds are giving us entirely new ways to observe the universe. They let us detect cosmic events that emit no light at all, like black hole mergers, essentially giving humanity a new sense with which to perceive the cosmos. For most of human history, astronomy has been a visual science. We've mapped the stars, photographed distant galaxies, and imaged black holes. But by adding sound to our cosmic toolbox, we gain an entirely new dimension of understanding. When astronomers sonify cosmic data, they often discover patterns they miss in visual analysis. As our detection technology improves, we're discovering that the universe is far from silent. And now, we want to share something special, what we call the cosmic chorus. This is a carefully arranged composition of all the sounds we've explored today, from the rumble of the Perseus black hole to the chirps of gravitational waves, creating a symphony of the universe, played across billions of light years and billions of years of cosmic history. That's the sound of our universe, not silent at all, but alive with acoustic energy, telling the story of everything that has ever existed or ever will.